Let us now move to the second part of today's lecture, which will be about optimization in the presence of constraints. And we will first cover so-called equality constraints, and only subsequently in next lectures we will cover also inequality constraints. So what is an equality constraint optimization? Essentially, we have an objective function like here that we would like to minimize, and it's an objective function where the decision variables are x1 and x2, so this was the standard so far. But this time we also add equality constraints, which says, for instance, 2 times x1 plus 4 times x2 must be exactly equal to 6. Okay? And we would like to find the minimum of this function subject to these constraints. And now here we can see that the constraints, they really dramatically change the position of the optimal point. Because if there are no constraints here, then what are the values of x1 and x2 for which the function is minimal? Give me the coordinates. 0, 0, right? However, 0, 0, like 0 here and 0 there, obviously does not satisfy the constraint. So the global solution without constraints is not equal to the solution with the constraints. Okay? So we can also look again at the contour graph, and we also know that these equality constraints, I mean, since they are linear, they form essentially a line in this space. So any feasible solution, first of all, has to lie on this line. If it is not on the line, it does not satisfy these constraints, and therefore it cannot be a solution. Okay? So we are essentially looking at the problem of finding a point on this line which achieves the minimal value, and the minimal value here is there. Okay? So we would like to find such a solution automatically. Okay? We don't want to plot it every time and then manually look for the optimal solution. So we need some automatic procedure, and actually we will cover 2 such procedures here. But first of all, we have to set up some nomenclature for this type of problems. So we would like to minimize objective function which is f. This is a function of decision variables, and we have small n of these decision variables. So this line here means that f is a function which maps the n-dimensional Euclidean space to one-dimensional Euclidean space. Essentially, it means the function takes n-dimensional vectors and it returns a scalar, because the objective function here is scalar valued. Okay? And we also have equality constraints. And for the equality constraints, notice that here on the right-hand side we have small m. Essentially, it means we can have multiple equality constraints. Okay? This m then means how many of these constraints do we have. Okay? So if we have 1 constraint, this would be 1. If we have 5 constraints, this would be 5, and so on and so forth. Okay? So that's the problem we will be looking at, and today hopefully we will cover 2 such methods for solving these optimization problems. The first one is the elimination method, and the second one is the so-called Lagrange method. Probably you have already heard about the elimination method. Well, I'm confident you did. So in the elimination method, and let me illustrate it on an example, which is the same. In the elimination method, we try to eliminate the equality constraints by expressing one of these variables as a function of the remaining variables. Okay, so here we have a constraint, which is our equality constraint, and we can express, say, x2 like this. Okay? And then what do we do then? I mean, what did we just achieve? Why did we do this? How does this substitution, I mean, how does it help us? What do we do with the substitution now?
We got it through variables, number of variables.
Yeah, so we substitute here, right? But we have to substitute everywhere. What happens if we substitute x2 here by this expression? What happens to this constraint? Now, let us check that. I mean, it's something which is very obvious, but Probably it's so obvious that you never even ask this question. So what happens if in this constraint I use x2 equal to 3 minus x1 over 2?
It will be always true.
Right, so we have 2x1 plus 4 times 3 minus x1 over 2, which is 2x1 plus, this one goes away, so that's 2, 3 minus x1, which is equal to 2x1 plus, and this must be equal to 6, right? This is 6 minus 2x1. Okay, so we end up with 6 is equal to 6. Okay? How do we call a constraint which is always satisfied? It is a so-called redundant constraint. So that means we can remove it because it is always satisfied. Okay? So what we achieved by this elimination is, well, by this substitution is that we eliminate this equality constraint. Okay? And then what we obtain is a new optimization problem. And there is something very nice about this optimization problem. It is unconstrained. Meaning we can solve the problem using our favorite method. We can solve it analytically. I mean, this is trivial. We just take the derivative. We could solve it numerically if we know we also know the gradient in this case, so we can use gradient-based methods. Or we could even use those gradient-free methods. I mean, who said that this function has to be differentiable, okay? If it is not, then we at least use those random-based methods or the estimation of the gradient, okay? So that's the idea, the underlying idea of elimination methods to solve equality constraint optimization. Get rid of the equality constraint by a suitable substitution. It must be a substitution such that the constraint becomes redundant, and then we obtain a new problem which is unconstrained. And this problem we can easily solve. The problem here is we only obtain x1 star as the optimal solution. Well, but then to obtain x2 star, we have to do the back substitution. So we take this and we plug it here and we obtain x2 optimal. Okay? And we can also double check whether it's really an optimum, so we can take the second derivative. So what does this say? If the second derivative is positive, what does it mean? Did we find the minimum of the function, the maximum of the function, or a saddle point of the function? Which of these?
Minimum.
The minimum, right. Okay. And then we can also, well, recover kind of the x2 optimal solution, and we can double check whether at the optimum the constraints are satisfied, and they are, obviously. Okay. So that's basically what elimination-based method is about. So let me give you a practical example. Your task is to design a packaging box which has several constraints. The first one is that this side here must be 4 times this side. The overall volume of the box must be exactly 200 cubic centimeters. And we would like to minimize the consumption of the material that is required to build up such box, but the box is open from above. Okay, so we are not counting this side here, but all others. Okay, and this is a typical problem of equality constraint optimization. Okay, so the problem that we are trying to solve is minimize the material consumption, which is just the area of the base, plus 2 times, well, these two sides, plus the front side and the back side. That's the objective function. And we have 2 constraints. Okay, A is 4B and the total volume is 200. Now, how do we solve this problem now using elimination-based method? We have to get rid of these constraints, okay? So the first one we can easily get rid of if A would be 4B. I mean, that's straightforwardly the substitution, okay? And what about this one here, right? So essentially, again, A is 4B, okay? So A times B would be 4 times B squared. Times C, that must be equal to 200. And from here we can, for instance, represent C, okay? We could represent B, but we would have a square root, and that's not so nice. So why not to express C, okay? And then what we do is we simply plug in A equal to 4B here, and C equal to this expression into the cost function. And we obtain a new problem, which is completely in B, and we have eliminated the equality constraint. And this problem we can rather easily solve, right? Can we? How would we solve such a problem? I mean, we have B in the denominator, so it is not so obvious. How would you solve this problem? How would you solve it numerically? Well, numerically meaning analytically, not using iterative methods, but really analytically. Okay, so we have the minimum of, and here we can kick out this term, so that's 4 times 50, that's 200 over B, plus 100 over B, plus 400 over B. Okay? So that's how much? Okay, so that's 700 over B. And we would like to minimize this. So what is the minimal value of 700 over B? There is something here which was not set a priori.
B cannot be 0.
Right, yeah. So here, it is not technically true that we only have equality constraints. I mean, we can also, implicitly, we also do have inequality constraints, okay? In these physical problems. And we usually handle them then when solving a problem like this. Then we ask ourselves, like, what is the solution with that added inequality constraint? Okay? But then if we add that constraint, we can find out the solution, and I guess you will do it in the exercises. Okay? And then, needless to say, once we have B star, we can recover A star from here and C star from there. Okay? So this is a real task, okay? That's a production system that we need to design, like to find out what are the optimal dimensions such that the volume is satisfied and we have a constraint like this. Okay? So, I mean, this kind of elimination, I mean, we have done it by hand. We have looked at those equalities and we considered, like, okay, what would be the best way of the elimination? But there is a way how to make the elimination some kind of an automatic process. And the automatic process, for that to explain, first we have to know how to write down a compact representation of these equality constraint optimization problems. Essentially, we have an objective function which is a function of several decision variables, and say we have two equality constraints like this. Well, first of all, what we can do is, actually here there's a mistake, sorry, that should be also x3 here. Okay? So we are deriving a compact matrix formulation of the constraints. So we are essentially separating the decision variables from the corresponding multipliers. Okay? So here, if this is x1, x2, and x3, then the first row is just this term times this one plus this one times that one plus this one times x3, which is exactly the left-hand side of the first constraint. Okay? So this just shows that, yeah, we typically write the problem in this form, that we compactly kind of summarize the equalities into Ax is equal to B. Okay? This assumes that all constraints are linear. In our box example, the constraints cannot be written in this form because they involve multiplication between decision variables. Okay? But very often the constraints are linear, and then they can be compactly represented like this. And now we come to the first kind of theoretical result of today's lecture. How can we eliminate these equality constraints? Before I give the answer, I give a simpler question. Imagine that this is an equality constraint. Okay? It's in the two-dimensional space, so we have x1 plus x2. And we know that this is a set of points which satisfies a1 times x1 plus a2 times x2 is equal to b. Okay? Actually, what if I tell you, let's have a constraint x1 plus x2 is equal to 2. And I ask you to draw me this constraint, draw me this line. So this is 0. Okay? Draw me that constraint. So to draw a line, we need 2 points, right? So the first point we can obtain when we set x1 equal to 0. Okay? So x1 is here. That means x2 is equal to 2, so that's 1 and 2. So that's our first point. The second point is when we set x2 equal to 0, well, we could set it to any value, but 0 is a nice value. So then x1 is equal to 2, okay? So it's like here. So the line, the equality constraint is like this. Now the question is there maybe an easier way how to draw this? I mean, look here. This is 2, right? This is a box. This vector here, there is a right angle between the line and this vector, obviously. There is, actually, I didn't have to go all the way there. It could also have been this vector, 1, 1. Can you see a vector 1, 1 somewhere? I mean, again, put this into this matrix compact form. That's 1, 1 times x1, x2 is equal to 2. There is our 1, 1 vector. And this is no coincidence. Actually, this one, if we then write it as ax is equal to b, then actually this matrix here, we call it the normal vector of the constraint. It's a vector which is always perpendicular to the constraint itself. Okay? So, and this will play a very important role in the elimination. So we have this vector which is 1, 1. Okay. And now I would like you to find all points on this line. Essentially, I'm asking you to give me the parametric representation of this line. To give me an expression which parameterizes the positions of all points on this line. How can you find all points on a line? Which information do you need? Let's suppose I give you one point.
And a parameter.
And a parameter and something more.
And the direction.
And the direction, precisely. Okay, so what is the direction? It actually doesn't matter. Okay, it can be this direction, it can be this direction, it can be this direction. All of them are the same. Essentially, I can find, so if I call this as some initial point x0, then I can find all other points as to the point x0, adding some alpha multiple of this vector here, of this direction, let's call it the d, okay? The question is, how can I find this direction here? Okay, here we have a specific example. What is the direction for this specific case? It is not 1, 1. It is some other vector. What is the vector? What is the direction here? So we are saying, what is this vector? And the vectors you can move around, right? So it is the same as this vector, okay? Which is -1 and 1. Okay? So the direction here, in this specific case, is -1, 1. Okay? It's actually one of the possible directions. Give me some other directions which are also suitable here.
Or linear combinations.
Or linear combinations, including the negative one. Okay, so it can have arbitrary size, and it can also go in this direction. Great. Okay. The question is, why took it so long to come up with this direction? There is one condition which is satisfied here, which will actually allow us to find this direction quite easily. What is the condition? Now look at this green vector, which is the normal vector of our equality constraint, so that's the green part. And now we have this red vector, which is here, and I can move it such that it is here, okay? That's the same vector. There is, these two vectors have some relation. And the relation is that, again, these two vectors are perpendicular to each other, okay? What does it mean that they are perpendicular? Well, technically speaking, it's called orthogonal to each other. When are two vectors perpendicular? Give me a condition. So I give you two vectors. I give you a vector A, and I give you a vector D.
When the vector multiplication is 0.
So A transpose D is equal to 0. Okay? So this has to hold. Okay? Does it hold in our case? So A, in our case, A is green, and A is 1, 1. Okay? Red is the direction, so that's D, and that's minus 1, 1. Okay? So when we multiply that, so we get 1, 1 times minus 1, 1, and that's trivially 0. Okay? So essentially, finding this direction means to find a vector which is perpendicular to the normal vector of our equality constraint. And actually this is a very standard operation, and it's called finding the null space of A. The null space of some matrix is a set of vectors which are perpendicular to the vectors in matrix A. Okay? So in MATLAB, if you would like to find this direction, you would just write the null of A, and it would return D here. Okay? So that was kind of a long introduction to what can be formalized as this. We would like to eliminate this equality constraint. We can eliminate the equality constraint by parameterizing all points lying on the constraint. To parameterize, we need direction, we need a particular solution, and we need some multiplication of the direction here. Okay? So what we say is, find some particular solution which satisfies the constraint. This is usually not the point in which the function is minimal, it's just some initial point. And then let us find a matrix F which satisfies this relation, meaning it contains vectors which are orthogonal to the vectors in A. Okay? And then let us define the parameterization as the initial point plus the alpha multiple of the vectors in F. The question is, why does this eliminate the equality constraint? So let us use that substitution. Okay? So what we have is, we know that A times x0 is equal to B. And the second thing we know is that A times F is equal to 0. Now, what we want to show is that this x equal to x0 plus F times alpha, the constraint Ax is equal to B is always satisfied. Okay? So how can we show that? Well, we substitute. Okay? So we have A times x0 plus F alpha. We want to check whether that's equal to B, always. Okay? How can we check that? Well, we expand. So Ax0 plus Af alpha, is it equal to B? And here we use the first property, which says the F is designed such that A times F is equal to 0. Meaning this term here is equal to 0. So we are left with checking whether Ax0 is equal to B. But also x0 was defined such that it satisfied this constraint. Okay, so it can be said that Ax0 is equal to B So that's why we have that B is equal to B. And that obviously is always satisfied, okay? So with this parameterization, we can remove the equality constraint. So that's what is said here, okay? Remember the reasoning why the constraint can be shown to be always satisfied. Now what? We have eliminated the constraint, so what do we do? We still need to minimize the function. But we are no longer minimizing with respect to x, but we will minimize with respect to alpha. Essentially here, it means find me by how much I have to scale this direction such that I end up in the optimal point. So I could kind of draw, for instance, the contour lines here. So let's imagine that the contour lines would be like this. And let's imagine that the function is also convex. Okay? We start by this point. Essentially what we are looking for is what is the value of alpha by which I have to scale this direction vector such that I end up exactly at the optimum. Okay? So the optimization now is with respect to alpha. We are not optimizing x anymore. We are only moving along the line, and what parameterizes the line are the alphas, not the x. x0 is a constant. Okay? So what do we do then is that we turn the optimization to an unconstrained optimization problem of this form. Simply we take the original substitution, we plug it in into the objective function, and we obtain a new problem which is unconstrained problem because the constraint was eliminated. It is a problem in alpha, so we can solve it using whichever method we like, and we obtain the optimum alpha. But we are not interested in alpha, we are interested in optimal x. Okay? But we have this substitution. I mean, we just plug it in and we are done. Okay? So this is a very general procedure which can be used to automatically eliminate equality constraints which are linear. Essentially, all we need to do is to find out this particular solution, x0, and this null space of the matrix A. And if we have the particular solution and if we have the null space, then we can solve the problem very easily. So in MATLAB, this is how you do that. Okay? So we have to find a particular solution. The trouble is that this matrix A probably will not be a square matrix. What would happen if the matrix would be square here? And I accept two possible responses. One is kind of more correct, more technically correct than the other one. What happens in this problem if you have A being a square matrix? What does it mean? You have as many constraints as you have variables. What does it mean?
So the constraints give us only a point, or some of them are redundant?
Right. So if they are all linearly independent and we still have as many constraints as variables, the solution is uniquely determined and there is nothing to be optimized. Okay? There is kind of a pathological case which says, okay, I could have two optimization variables and I could have my matrix A being like this. So imagine that the constraints are, for instance, this one. Okay? This also has as many constraints as variables, but they are linearly dependent, these constraints. That means here, technically speaking, just one constraint. Okay? So when somebody asks you, like, what happens if the matrix is square? Well, you cannot answer unless he also tells you whether the rank of the matrix, meaning the number of linearly independent rows, is also equal to the number of decision variables. If it is, the solution is uniquely determined. We could even have more constraints than we have optimization variables. And again, if all are linearly independent, then how many solutions do we have?
One or even zero.
If we have more constraints than optimization variables, and all constraints are linearly independent, then we have no solution. Okay? So that's why we only consider a case where A actually has fewer rows than columns. Okay? which means this system of equations, just looking at the constraint, has infinitely many solutions. So what this does, it finds at least one of such solutions, which is consistent with Ax is equal to B. And the second command that finds the null space of A. So that's an automatic way of finding those orthogonal vectors. And there are more efficient ways how to obtain both the particular solution as well as the null space using, for instance, QR decomposition methods, but they are not so important here. Okay? The bottom line is we could get the particular solution and we could get the null space. Okay? So let us verify this procedure on the following example. How can we solve it? Using what we said here and what was the geometric interpretation. So remember, we are going to eliminate this, this constraint, which is Ax is equal to B, where A is 1 minus 1. We have two decision variables, x1, x2, and that's equal to 2. Okay, so that's A. And we need x0 as any particular solution of this system of equations. And we need f as a matrix which satisfies A times f is equal to 0. So give me one particular solution of this system of equations. Any.
So we can set x1 to 0 and x2 is minus 2.
x2 would be minus 2. Yeah, that's one option. Great. Okay. Here I use like 5 and 3. Okay, which is the same. Okay. What is then? So that's this one. What is then the null space of A? Give me a vector which is orthogonal to vector 1 minus 1. Right. Okay, 1, 1. That's trivially orthogonal. Okay. What next is that we do this substitution. Okay, so we have x0 plus f times alpha. Okay. Now we need to plug it into our original cost function. How would now the modified cost function looks like? So we, essentially what point number 3 means is that x, which is x1 and x2, is equal to, and now I can put those two together. So the first coordinate is 5 plus alpha, and the second one is 3 plus alpha. Okay? So this is x1, this is x2. So if you want to minimize x1 squared, we are minimizing this guy squared, right? So that's 5 plus alpha squared plus 3 plus alpha squared. Okay? What is the optimal solution here, by the way? Give me optimal alpha which minimizes this cost function. It's a sum of quadratic functions. The minimum can be at 0. Okay? Which value of alpha gives the minimum as close to 0 as possible? How would you find such a point? Yeah, we would make a derivative of the cost function. Sorry?
Minus 3.
Minus 3 minus.
So we have, that's the expansion, okay? So it's actually minus 4. Okay? So we make the derivative which is a times alpha is equal to 16 and not just 16, it's 16 plus 34, okay? So that's why the optimal alpha is minus 4. And we can recover the optimal x from here. Okay? And that's our optimal solution with respect to this original problem. Okay? So that's how these problems are solved. First, find out a particular solution. Then find out the null space. Make the parametrization. Plug in the parametrization into the original cost function. We don't have to consider constraints because they were eliminated using a suitable choice of x0 and the null space. Solve the problem with respect to alpha and substitute back, obtain the original solution. And here, when solving the problem in alpha, you can use any method you would like. Okay, you can use the analytic method, you can use numerical methods, whatever. It's up to you. Okay? Good. What about this case now? Let us add a new variable, x3, into the problem. And here I would like to illustrate something. Okay, so first of all, give me a particular solution. So what is now the particular solution?
It is a plane.
Just one particular solution, any. So as you said, it was 0, for instance, here.
Yeah.
That would be -2. And what about x3? Arbitrary. Whatever, right? Okay. Now comes the tricky part. Give me the vectors which are orthogonal to the constraint. The constraint is 1, -1, 0. Okay, so we are looking for vectors whose dot product with the A matrix is equal to 0. Give me such vectors. What would you use as a null space here? So give me one vector. Essentially what we are looking for is a vector, say f1, f2, f3, such that this product is equal to 0. So obviously we can choose, for instance, 1, 1, 0, right? That's satisfying. The problem is this is not enough. There is something more. There is one more fundamental vector.
Whatever.
That's already here, 1, 1, whatever. There is something more. There is something, once you see whatever, you see that you require something more. Essentially, the other one we are looking for is 0, 0, 1. Okay? Because this one will also parameterize x3. Okay? This one was not able to parameterize x3. Essentially what happened here was that imagine that you are in the 3-dimensional space, and imagine that the constraint, if we have two constraints, then it would be this plane. Essentially it would be this one. There is only one vector which is perpendicular to both. It's this one. Okay? But now we are saying something more. We are saying we are in 3 dimensions, but we have only one constraint, which means that the constraint could be, it is not in this particular case, but it could be, for instance, just this single line, just this single axis. And here we have two principal vectors which are perpendicular to this axis. It's this vector, because there is a right angle there, and it's this vector because there is a right angle here. Okay? So we need to actually, as a null space, we need to consider all linearly independent vectors which have right angle between themselves and the vector in the constraint. Okay? So that's why, that's why we have to be a little bit careful here. And we have used the word linear independence a couple of times, so just to remind you about the formal definition. So let's suppose we have a matrix V, and each of the columns is linearly independent if the rank of the matrix is equal to the number of columns. Okay? And the rank is the number of linearly independent rows and columns. So this probably you know. So what is the rank of this matrix here? Why?
Because the 2 rows and the 2 columns are linearly independent.
Precisely that, thank you. Yeah. They are linearly independent. What about this one? Can we see some linear dependence between the rows or the columns? No. So also rank 2. This one? Are these either rows or columns linearly dependent? Linearly dependent means if I take one row or one column and I multiply it by anything but 0, I can add them up and I obtain some other row. Okay, so here, yeah, so we can multiply, for instance, the second column by 2, actually minus 2, and we would obtain the, okay, by 2, and we will obtain the first. So it shows that the second column is just a linear combination of the first one. Okay, so the rank here is 1. Okay, here.
Because the first and the second row are linearly dependent.
Precisely, and you can also say the constant if somebody asks you, but it's not so important here. Okay, this one. So here, I mean, we will not find a direct relation between any of two rows. But what we can do is, while checking linear dependencies, we can combine several rows and several columns together. So for instance here, if we multiply the second row by -1, and we add to it the first row, then we would actually obtain the third and final row, which shows that the final row is some linear combination of rows number 1 and 2, which shows that the rank cannot be 3, and actually the rank here is 2. Okay? Can we achieve something like that here? Actually, what I did is I've just changed the final component from 0 to 1. Do there still exist some multiples of the first row and the second row such that when we add them up together we end up with the third row? No. Okay, so here the rank is 3. Okay, so that's what we have in mind when we say we are looking for linearly independent null vectors, so orthogonal vectors. They have to be linearly independent, as we have in that case. Okay? So this could be our choice of the null space. Actually, the choice of the null space is not unique. There are infinitely many choices because we can arbitrarily scale these two vectors by any non-zero constant and still have the property that A times F is equal to 0. Okay? So this choice is not unique. Actually, what MATLAB will return here, it would return something like the square root of 2 divided by 2 here, and the same there. Essentially, it is returning the vectors which have unit size, the size of the vectors being equal to 1. Okay? That's kind of one choice from that infinitely many vectors. So don't be surprised that in MATLAB you will see strange things here. Always verify whether A times F is equal to 0. That's how you check whether this is really a null space of the equality constraints. Okay? And we can do the same thing as before. Okay? Meaning we parameterize X as the particular solution plus the null space, but here is what I want you to stress. We have now 2 null vectors, therefore we need 2 alphas here, not just 1 but 2. Okay? So the number of optimization variables is always equal to the number of columns of the null space. In the previous case, the null space was just 1 column, therefore it was just 1 alpha. Here we have 2 columns, therefore we have 2 alphas that we need to solve for. So what do we do then? How do we transform the original optimization problem now? Tell me, which problem would you solve if you would be facing this issue? So X, which is X1, X2, and X3, is equal to particular solution plus the null space times alphas, which means that X1 is 2 plus alpha 1, right? X2 is just alpha 1, and X3 is just alpha 2. Okay? And now we need to plug it into our cost function, meaning we are minimizing x1 squared. X1 is this guy. So 2 plus alpha 1 plus x2 squared, which is just a1 squared, plus x3 minus 1 squared, where x3 is just alpha 2. So alpha 2 minus 1 squared. This one, yeah, thank you. Yeah, there should be a square there. Okay? And these are non-constrained optimization problems in 2 decision variables. So we can easily solve that using analytic methods, and this would be the optimal solution. Okay? And then once we have the optimal alphas, we plug them back, and what we obtain is the optimal solution with respect to x. By the way, notice that if we would omit the final column, okay, pretend that we didn't include all necessary null vectors, then essentially